Okay, in this video, I thought we would talk about the problem of the cascode bias voltage and picking a cascode bias voltage that's appropriate for a given input current level. So I'm starting out here in the simulator, and we have a way of generating a gate voltage that's appropriate to make a transistor pass a given amount of current, and that's the diode connection. Right. So if we want to make, let's say, the nominal current level, saturation current level in this branch here be 1 microamp, which is about the threshold current for these type of devices we've been working with, we force a microamp of current into a diode connected transistor that's matched with the transistor we want to produce the microamp in, and we form a current mirror. Okay, this is not surprising at this point, hopefully. And what we would like to do by the end of class today is to figure out, is there a circuit that we can use that would be maybe a little bit more complicated than a diode-connected transistor? It'll actually turn out to have some diode-connected transistors in it that will basically be able to generate a good cascode bias voltage, and we'll see what that means here in just a minute. So the first thing we want to do is try to see what effect having different cascode bias voltages have on the performance of this cascode configuration. So we're going to sweep the output voltage here, measuring the output current for several different values of the cascode bias voltage. So I'm going to, edit the simulation command, and I want to sweep VC. I'm going to make it a list, and let's do 2, 3, 4. Okay, so let's run this. And we're going to tile these vertically. And you can see here what looks to be a drain characteristic, okay, where we have the ohmic region down here. It shoots up. But we have this kind of funny situation where we have these 3 different curves that are mostly on top of each other here, but then they peel off and become flatter here. And if I zoom in here, you can get a better picture of what's going on. You can see that we have sort of one slope going on here, and this is the RO slope, the ordinary early effect resistance of the transistor. And you can see that this looks like a huge change, but it's only going from like 0.98 microamps up to 1.03 microamps, which is a change of about, 4%, something like that, 5%, which is what we kind of expect for the early effect. But what happens here is that these flatten out at different places. So this is the 2 volt VC, the 3 volt VC, and the 4 volt VC. And so this is actually the output characteristic with the cascode transistor in play. So this is what happens when the bottom transistor is just, the drain voltage V of that bottom transistor is just being swept out as we sweep V out. So if we were to look at the node voltage V, we want that. I would like to click on node V. We can see what V is doing, see what V out is doing. And so let me also zoom in on output current here. No, that's not what I wanted to do. It's also zooming in on that. So let me zoom this back to fit. Anyway, so we can see here, here's the output voltage that we're sweeping. This is just the identity line. And this is the voltage V for the 4 volt simulation, the 3 volt simulation, and the 2 volt simulation on VC. And you can see that this very flat part of the drain characteristic corresponds to the distance between Vout and this voltage V being quite large. And you can see that as Vout is changing, this voltage is basically being held constant by the Cascode transistor. But the corresponding point where there's a knee in this curve is where the Cascode transistor falls out of saturation. And when it starts falling out of saturation, what we go is deep into the ohmic region, and eventually we get very, very little voltage drop across that Cascode transistor. It's just a little tiny bit of series resistance. It might as well even not be there, or might as well not even be there. It's not doing us any good, really. And what we're doing when we sweep V out is we're just sweeping out the drain voltage of U1. And eventually we get down to the point where U1 is in the ohmic region. And so there's these sort of three distinct regions of the curve. There's where both the Cascode transistor and U1 are in the ohmic region. There's this part of the curve where U1 is now saturated, and we're moving up its saturation characteristic. But U2 is still in the ohmic region. And then when we hit U2 in the saturation region, that's when we have the full benefit of the Cascode transistor, and we get a much flatter output characteristic. And so you can imagine that the optimal place that we would like to bias the Cascode voltage is whatever value of Vc would basically make this intermediate region where the Cascode transistor is in the ohmic region and the transistor being cascoded is in the saturation region down to 0. Okay, so if we were to maybe repeat the simulation with Vc of, let's say, 1 volt or 1.2, and run that simulation, you kind of get to the point where, if you look at this, you can imagine that that region where the Cascode transistor is in the ohmic region and the transistor we're cascoding is in the saturation region is practically 0 at that point. Okay, I'm not claiming 1.2 is the optimal value in this particular case, but it's pretty close. I mean, we really can't see that intermediate region there very clearly. It just kind of blends into both transistors falling into the ohmic region. And so an optimally biased cascode would be one in which this flat region extends down as far as possible, and the Cascode transistor and the transistor we're cascoding with it are both coming out of saturation at the same time. Okay? So that's what we're going for. And we'll return to the simulator in a little bit, but let's see, go back over here to the whiteboard. And so we're going to talk about Cascode bias voltage generator. Okay, and so the first thing we're going to do is we're going to start out with a couple of transistors here. Actually, let's start out even with one transistor. All right, so we have a transistor, and it's got some current I, and we got a gate voltage here, a source voltage, and a drain voltage. And just to remind you, we model the current flowing through this transistor as the difference between a forward current, IF, and IR. And on the EKV model, we have specific forms for IF and IR. IF would be equal to SIS times the log squared of 1 plus e to the kappa Vg minus Vt0 minus Vs over 2ut, and IR is equal to SIS times the log squared of 1 plus e to the kappa Vg minus Vt0 minus Vd over 2ut. Okay? And in saturation, we have this notion that IF is much bigger than IR. So ISAT is basically approximately just equal to IF, and it's independent, not equal to a function of VD. Or it's independent of VD. In the ohmic region, we have IF basically being approximately equal to IR, so they're on a par with each other. You know, IF is probably larger than IR somewhat, but they more or less cancel, and so I is down near 0 amps and is roughly proportional to VDS. And if we were to, if we wanted to, we could sort of define operationally saturation as some particular place where the ratio between IF and IR achieves some large number. So we could define the onset of saturation as, or in terms of, IF to IR, that ratio is equal to some large number A, where A is much bigger than 1. So if we do that, if IF is, let's say, 100 times bigger than IR, then we might say that IR is negligible compared to IF, and so that the current is just the saturation current. That's kind of what we're going for here. So we can take this ratio of the forward current to the reverse current in a given transistor as a measure of how close we are to the onset of saturation. That's going to be a key idea here for us. Okay? So let's take a pair of transistors. This marker is tired. Let's take a pair of transistors connected in series, and so they have a common gate voltage, which we'll call VG. And let's call the current flowing through this one, I'll call this one M1 and M2. I'll call this current, say I1. And let's say we're injecting a current in here. And let's call this voltage here V. And we'll call this current here, let's say I3. And let's call this current here I2. Okay? So now we're going to assume that M1 is saturated. So whatever this voltage is up here, it's high enough above V to guarantee that M1 is saturated. But M2 is possibly ohmic. Okay? And we're going to also assume that the transistors are matched. Standard assumptions. Assume M1 and M2 matched, same temp, and no early effects. So VA goes to infinity. Okay, and we'd like to just get a handle on what's going on here. Okay? Eventually what we would like to do is we would like to figure out what is the sort of saturation index that we just talked about for transistor M2. Okay? What is IF2 to IR2? That is what we are going for. Okay? If IF2 to IR2 is large compared to 1, then this voltage here, V, between the two transistors, is going to be close to the saturation voltage VDS sat, 1 VDS sat above ground. Okay? That's the basic idea. So we want to figure out what is this ratio dependent upon in this particular configuration. Okay, so we said that M1 is saturated, so we know that I1 is basically equal to IF1. Okay? M1 is saturated, so I1 is equal to IF1. So M1 sat. Now, we also know that I2 is equal to IF2 minus IR2. Okay, that's just saying that we can decompose the channel current in M2 in general into the difference between a forward current component and a reverse current component. No big surprise there. We also know from KCL that I applied at node V that I2 is equal to I1 plus I3. And this marker is feeling tired. So let's try that again. I2 is equal to I1 plus I3. Okay. Now, the other thing to note is that M1 and M2 have the same gate voltage. And they also share one source drain region in common. Right? So the source of M1 is node V, but the drain of M2 is node V. Right? So M1 and M2 have the same gate and a common source drain region. So we have from that the forward current in transistor 1, which is equal to basically IS times log squared 1 plus e to the kappa Vg minus Vt0 minus V over 2ut is equal to IR2, right? So these two things will have the same form because they have the same gate voltage and they have the same source or drain voltage. Okay? So we have here from this equation that this is equal to I1. Right, so IF1 is equal to I1 is equal to IR2. So that implies that IR2 is equal to I1. So, if you like, that's equation 1, equation 2, let's say. So, 1 substituted into 2 tells us that. And if we take this as equation, let's say 3, we find, if we divide both sides of equation 3 by IR2, we find that I2 divided by IR2 is equal to IF2 divided by IR2 minus 1, or the thing that we're looking for, IF2 divided by IR2 is equal to 1 plus the ratio of I2 to IR2, which we know is equal to I1, which is equal to 1 plus I2 over I1. If we call this equation 4, if we plug equation 4, which is KCl, into 5, we find that the thing we're looking for, the saturation index of transistor 2, IF2 to IR2, in this particular case is equal to 1 plus I1 plus I3 over I1, which is equal to 2 plus the ratio of I3 to I1. Okay, so this is interesting. So we have these two currents that we're forcing in here, possibly. And if we wanted to, we could actually set I1 by doing the following. So if we take a current source, I1, and then we take M1 and diode connect it, that gives us two things. That gives us the ability to set I1 with an external current source, and it also ensures that M1 is operating in saturation. All right, because diode connected transistors operate in saturation. And if we make I1 much smaller than I3, then we can set this ratio of IF2 to IR2 to be anything we like. If we make I3, let's say, 100 times bigger than I1, then this ratio would be 102, and V would be very close to a saturation voltage above ground. So if we set if we make I3 much bigger than I1, we have two things. One, V is approximately VDS set. And notice I2 is approximately equal to I3. So because I1 is much smaller than I3, I2 will be pretty much the same as I3. Okay? So that gives us a way of generating a voltage VDS set above ground. And that's where we would like the node voltage between the transistor that we're cascoding and the transistor that is cascoding it, where we would like that to be optimally. Okay, so suppose, take this out. So suppose we're cascoding a transistor here and the current is going to be let's say it's comparable to I3. Let's say it's I out. This is V out. Let's say I out. Oh. We would like this to be about VDS set. And let's say that this is well, let's say this is VG, right? So that this current I out is basically I3 or I2. And so what we'd like to do is figure out how can we generate this voltage VC so that given this voltage here, V, which is about VDS set, we'd like this to be about VDS set. We want VC to be just high enough above that given the current that it's passing to allow this transistor to have its source voltage here at VDS set. I guess that's what I'm trying to say. Well, we can do that by passing that current through a diode-connected transistor that's sitting on top of this voltage V. So we're still injecting I3 onto this node, so we haven't changed anything about what we said down here. And so V will still be about VDS set. But now we're taking I3 and we're putting it through a diode-connected transistor, and this diode-connected transistor says, okay, given the source voltage is set up by this other circuit here, how far above that do I need my gate voltage to be for this type of transistor to pass this current? And that's precisely, that VGS drop here is precisely the one that we need to compensate the VGS drop of the Cascode transistor. Okay, so this is our basic Cascode bias circuit. So if we have some current level that we would like to produce a Cascode bias voltage for, we can put it in here. And we can take a current that's much smaller than that, either a fixed current that's much smaller than that, or a current that is divided down to be in some fixed ratio between that and in that, and basically produce a cascode bias voltage. Okay, so let's flip back over to the simulator. And let's close this one down. Alright, why not? And here, I have the same circuit I had before, only now I have put together here the cascode bias circuit that we just talked about, and I've defined my current here in terms of a parameter, which is going to be the same as the current that's being put in here. And then I'm defining this current as that input current divided by some number n. I've also put in place here a parameter for the multiplicity of U5. It turns out that we can actually, by making this transistor have a ratio with the other transistors, so these are unit transistors, and this one could be like 2 or 3 devices connected in parallel with each other, so it's a little bit wider. We can actually also, by making m greater than 1, we can basically multiply that saturation index by m, if you work that out. And I didn't go through the math, but we can see what that does here. And so what I'm going to do is run the simulation and tile them vertically. And it is giving me, why is it giving me power meter? Alright, see if I can actually get what I want here. That's not what I want. Alright, let me close down LTSpice and run LTSpice again. Load this up and let us edit mstall so it's a picoamp. And let's run the simulation. Boom. Tile vertically. Yay. Can measure the current. Awesome. So you can see here this drain characteristic of the cascode is quite flat. It's not maybe quite as flat as the cascode where we're biasing U1 further into saturation, but it's pretty darn flat, especially compared to the transistor's normal drain characteristic by itself. We can also look at input voltage, or the output voltage, and what's happening with the node voltage here, V, that's intermediate. You can see that it's basically down here at about 0.2 volts or so, 0.15 volts, something like that. So that's pretty much a saturation voltage above ground for this particular current level. And we can see what the cascode bias voltage is. It turns out it's about 1 volt in this particular, for this particular current level. And we can see that there is no visible place where we have that kind of intermediate slope with a kink in the curve where it flattens out here. And we can play with these numbers here. We could make m equal to 2. And rerun it. And this is maybe a little tiny bit flatter. can see the cascode bias voltage is a little tiny bit higher, not that much higher, but it does make a little bit of a difference. You can make M 4. And this is maybe again a tiny bit higher, so we're biasing U1 a little bit further into saturation. And so this circuit turns out to be a very nice cascode bias generator. So if you're making, for instance, a mirror cascode amplifier, the transistor that you're cascoding could have a current that's going between, let's say, 0 and the full bias current in the diff pair. And so it would be appropriate to set the cascode bias voltage so that it's optimal for the maximum current that could go through as the diff pair switches back and forth, which is the bias current. So you might use a circuit like this to be to generate the cascode voltages for the NMOS transistor off the bias current for the diff pair. You can also flip the circuit upside down and use it to generate cascode voltages down from VDD very easily. In that case, you may need to use some current mirrors to generate appropriate mirror copies of the bias current, turning it around. All right, so this is a way of generating cascode bias voltages. You can see it's a little more complicated than just a simple diode connected transistor, but it's not too much more complicated. Okay, I'll send you also a link to a paper that you can take a look at that I wrote, a conference paper quite a long time ago now at this point, on this circuit as well. So hopefully that was interesting and maybe even useful. So I hope you all enjoyed this. This is actually the last video that I'm going to do for the class this semester. It's been a real pleasure having you guys in class. Sorry that the situation the last half of the semester has been a little weird. Definitely not my preference that we would do things remotely, but hope it's been tolerable, and it's been a pleasure having you all in the class, and hope to see you around campus in person next year. And we'll see you in Zoom land as you work on your projects and finish other stuff up in the next week or so. Okay. Take care.